Hey everyone, so this is 4.1, Graphing Polynomial Functions. So we are now starting with polynomials, which are a bunch of monomials or a sum of monomials, as you can see the definition right there. And in case you are wondering, a monomial is actually a number, a variable, or either, a variable and a number together, as long as the exponents are whole numbers. So a polynomial is a monomial or a sum of monomials. So you can have a monomial be a polynomial as well. So that would look something like, for example, 3x squared, right? So those are the key points of a polynomial or a monomial. This 3 represents the leading coefficient, which, normally we would just call it a coefficient, but in terms of a polynomial function, it's important to identify the leading coefficient. And we'll talk about that later. Then I have my degree, which is very, very important. Okay, so the degree is the exponent of the monomial. Now, a polynomial function is a function in the form. Now, this form here looks very, very intimidating, but in actuality, it's really just saying that n is your highest exponent, your highest degree, and an actually just represents the coefficient attached to that, and so on and so forth. Polynomial functions are written in descending order. So if you had, for example, n equal 5, your next term would be n minus 1. So 5 minus 1, which would be 4, 3, 2, 1, until you get all the way to the end. So if I wanted to write this in terms of numbers, right, I would have, I'm not going to start too high. We're going to say 3x cubed plus 2x squared plus x, and then plus 7. Now this 7 actually represents another important term we need to talk about, which is the constant. Okay, so that is when technically your variable has a power of 0, right? Anything to the power of 0 is just 1. So that makes it the constant. Okay, it is the constant term. It's also the y-intercept, right? Because if everything else has an x, when you have x equals 0, the leftover will be the constant, which is your y-intercept. So as a little fun fact, that is also your y-intercept. So now we have very common polynomial functions. So as I already said, polynomials, monomials can be polynomial functions. So functions that we're actually used to, that we've talked about already, right? Constant, linear, and quadratic. We haven't talked about those last two, but we will get started with those. So a constant would be something like negative 14, right? Any kind of number, 7, 12, 11, whatever you want, that's the one you're going to see. Now, I'm using the examples found in your textbook. There's a chart there that if you wanted to look back on it, you can. They also have the standard form, which would just be, I'll write the standard form in purple, would be represented by f of x is equal to a 0. That's what that's 7. This number, this a0 over here, this 7 over here, that's your a0, that is your constant. Okay, now a linear function, we are all used to that, right? That's that y equals mx plus b. So 5x minus 7. So in standard form, that is a1 x1 plus the constant. I don't have much space. So if you can't see it, because I'm probably not going to have enough space with these last few functions, but you can always see if I make some more space. You can always check your textbook. I think the most important part is the actual example of what it looks like more than anything, because you're not going to see it in terms of a1x plus a0, right? We're going to see it in this standard form here with the actual terms and values. Now, a cubic function is a degree of 3, right? And if you want to think about it, when you do volume, for example, right, in science, your units are always cubic units. So cubic is to the third power, and then a quartic is actually to the fourth. So x to the fourth plus 2x minus 1. Now, as you can see, those are our common polynomial functions. They are not things that should be unfamiliar to us. Cubic and quartic might be the most outrageous ones that you've seen, but still, we won't really go past quartic when it comes to graphing, but you'll notice a specific pattern as we continue. Now, identifying polynomial functions. So the first thing I need to do when it comes to this is I need to make sure that what I'm looking at is a polynomial function. And to do that, I'm going to actually jump back over here and highlight these key points. So these key points here tell me a of n cannot equal 0, the exponents are all whole numbers, and the coefficients are all real numbers. So those are the important facts that I need to know about when it comes to something like this. And actually, I should unhighlight that when I upload it on Schoology. You don't see those there. Okay, so the first thing you want to do is determine if it is a polynomial. And to do that, I'm going to check my degrees. So in this first one, I have a degree of 3, I have a degree of 4, and those are both whole numbers, okay? Now remember, whole numbers are numbers like 1, 2, 3, 4. I believe whole numbers include 0. But we can't have a equals 0. We also don't want the exponent to equal 0, but that would still qualify as a polynomial function as long as these are all whole numbers, no fractions, no decimals, nothing like that. So this one here is a polynomial, so checked out. Now I need to write it in standard form. So remember, like I said, standard form is in descending order. So you need your largest variable to be first, which in this case is that square root of 2x plus n times x to the fourth. So square root of 2x to the fourth. Now you may be confused about this, but remember that the square root of 2 is still a real number, right? That is the only requirement for the coefficients. The coefficients have to be real numbers. So the square root of 2, although it is going to be, I don't remember if it's a repeating or if it's one of the irrational numbers, but a real number it is. So remember, if it were a negative 2, then we would not have a polynomial. So I'm going to just keep going. And minus 12. So now this is in standard form, and I'm going to identify a degree, which my degree is the largest exponent, so it's a degree of 4. The type, so this is actually if it's to the fourth power, it is a quartic. And then, actually, I cut off the last part. We need to identify the leading coefficient, which in this case, I'm just going to call it the LC. And that's probably too close to the edge. The LC is, oh, that's not a good spot either. The LC is the square root of 2. This is my leading coefficient. It is the number attached to the x4. Now, I'm going to look over at my second example right here. We have negative x squared plus 7x to the negative 1 plus 4x. Now, I am going to determine if this is a polynomial. So my degrees are 2, negative 1, and this is technically a 1 right there. However, this is not a polynomial function. I don't know what that meant. This is not a polynomial function. Why? Because negative 1 is not a whole number. Remember, whole numbers do not include negatives. The only thing that includes a negative in the family are integers. So this is not the requirement. The requirement is that the exponents are all whole numbers. So that one is ruled out. And then I actually don't have to do anything else because it doesn't matter. So moving on, evaluating a polynomial. So The steps for evaluating a polynomial are the same thing that you have been doing since Algebra 1. They give you an x value, you plug it in. That's all you have to do. So in this case, I am looking for when x equals 3. That's what this f of 3 represents. It's telling me replace x wherever, a 3 with wherever I see x. So I have 2, 3 to the 4th minus 8, 3 squared plus 5 times 3 minus 7. So I'm going to do 2, and off the top of my head, 3 to the 4th. I'm not sure, but if I'm going to have to. So 3 to the 4th is actually going to be 81 minus 8 times 9 plus 15 minus 7. Now, I don't want to combine the 15 minus 7 just yet. I just kind of want to leave it there until I've gotten everything else figured out. So 81 times 2 is going to be 162 minus 8 times 9 is 72 plus that 15 minus 7. So when I combine all of these together, and I should have changed colors, now I'm going to have to do it or it will bother me. So I had 2 times 81 minus 8 times 9 plus 15 minus 7. Right. And then I will rewrite it. 162 minus 72 plus 15 minus 7. And then when I combine all of these, I end up with that it equals to 98. And that's it. That's how you solve for a polynomial. Again, it's nothing different. It's nothing that you haven't done before. It's all the same. Now, end behavior of polynomial functions. So this chart that you have in this column is incredibly, incredibly important, and I would highly recommend that you memorize it as soon as possible. Okay. Now, this is going to tell you how your graph is going to look on the ends. So this is very helpful when it comes to describing the function, or if you're looking to sketch the graph, it is good to know the end behavior so that way you are able to kind of figure out what to do. So you can see you have when your degree is odd, when it's even, and when your coefficient is positive and negative. So there are the 4 main types of end behavior, and it is always good to recognize what it is. Now, let's say I have here, in describing the end behavior, I have a function f of x equals negative 0.5 x to the 4th plus 2.5, oh, I'm going to run out of space. So let's try this again. Negative 0.5 x to the 4th plus 2.5 x squared plus x minus 1, right? Now, I don't really need to do anything if I'm just talking about the end behavior. What I want to do first is determine the degree of my function. So I look for the largest exponent, that is 4. So my degree is 4, meaning it is an even number, right? Then the next thing I need to do is look at the leading coefficient. My leading coefficient is negative 0.5, meaning that it is a negative term, right? So now I'm going to go ahead and I'm going to look at my chart, and I'm going to look for the one that says even and negative, right? So whenever you have an even function, just as a little hint, even functions always end in the same direction, okay? Think of the parabola, right? It is a U shape. So what's happening is that's going in the same direction. So a quartic, which is also an even number, is going to look something like that. It's not going to be perfect. It can obviously have different values, but that is the general idea, that the end behavior of your function is pointing down. Now, as you can see in the chart above, you have some very interesting terminology, right? So I kind of don't like the way the book has this. They actually start with the Y, but it is much more common to see the end behavior written as x approaches negative infinity, your f of x is approaching. So I would look at my graph and look at how the graph is going as my x values turn negative, right? My y values turn negative. So they are going towards the negative. And then as my x is approaching positive infinity, my f of x, so once again, as my x terms are moving to the positives, my y is still going towards negative infinity. So I will say one of the most difficult things for us to remember is that this, as x approaches negative infinity and as x approaches positive infinity, those you should consider it as a template. Okay, when you are discussing end behavior, you are always going to say, as x approaches negative infinity, y approaches something. This part here is your real answer. That is really what you are filling in. Everything else is default. That is how you are supposed to write end behavior when you are answering questions regarding end behavior. Okay? Now we're going to look at graphing. So this is where it comes into play, the end behavior and the various information that we just learned about all these functions. So I have here a function. Now, first of all, I'm going to notice that it is an odd degree and my coefficient is -1, but I'm going to kind of put that in the back burner right now because that's step 2. So the first thing I want to actually do is figure out how I'm going to graph my function. Now, I'm not going to spend too much time with this. If we need to review graphing, please let me know when I am back so that I make sure we know how to graph. So the first thing I'm going to do is create a table of values. So remember, when it comes to creating a table of values, you are picking the values, okay? You pick whichever points you want, and that is what you are going to use. Now, I would advise you not to pick crazy numbers, right? Don't go ahead and do 100 or 72 or things like that. Try to keep them simple. I always recommend going a little bit into the negative and a little bit into the positive, right? Now, I'm going to actually do -2, -1, 0, 1, 2. If you are going to do -2, -1, always have the positive version, right? You should have the negative and the positive version, and always include 0. Now, I'm hoping that we all know what we're supposed to do, right? You are going to plug in the values and solve for y. So just quickly, for example, I'm going to actually end up erasing this. If I were searching for, I want to do 0, it's like the cheating one, but let's say I did 1, right? So I would have 1 cubed plus 1 squared plus 3 times 1 minus 3. So that would be -1 plus 1 plus 3 minus 3. And then when I solve for that, I would actually end up with 0. Okay, so I'm not going to go through that. If you need me to go through that, like I said, please bring it up to me when I'm back and we can go through that. Right now, I'm just going to fill in. These are the points, as the same points that are used on the textbook. So I'm just going to keep it simple and just fill in the answers right. So now I'm going to plot my points. So I kind of have here my function. So at 0, I'm looking at -3. So there's 0, -3. And then I have 1, 0. And then I have 2, 2, -1 is going to be a little bit in the way. So I'm actually going to move this 1, 0 up here. 2, -1. and then -1 to -4. And then -2 to a +3. So that's kind of what my graph looks like. Now it's a bit odd to see it set up like this, but now I'm going to figure out my end behavior. So like I already said, my degree was even. Oh no, I'm sorry, odd. A degree of 3 is odd, and my leading coefficient is negative. So if I look back at my chart, which is over here, an odd degree that is negative, notice how my quadrant 2, right, because this is quadrant 1, this is 2, 3, and 4, so on and so forth. If we need to go over that also, you can bring that up to me. In the second quadrant, my y values go towards the positive infinity, and in the fourth quadrant, my values are now going into the negative. So my end behavior is basically going to be something like this and something like that. Now I'm going to go ahead and kind of graph it. So knowing that my directions, I'm going to kind of, it doesn't have to be perfect. This is just getting me an idea of what my function should look like. Now a cubic function does look like this, or an odd cubic function, or a negative one looks like that. So my shape, it's a little funny, but it is the correct shape. Maybe I can cheat and make it look a little bit better. Let's see. Nope. All right. So there it is. There's my function. Looks great, right? And that's pretty much it. That's how I'm going to graph it. Now, when it comes to sketching, so sketching is a little bit different. It is much more inaccurate, right? But I don't think it's that difficult to do. It does require a lot of, I don't want to say problem solving, but it's definitely a lot of logic you need to apply. I actually need to grab that example. It is all messed up. Right, then I will write in the information. So my information on the graph that I am looking to sketch is the first key is that f, remember f is just your y values. F is increasing when x is greater than 0 and x is less than 0 and x is greater than 4. Okay, so I need to keep that on my mind. Then f is decreasing when x actually lies between 0 and 4. So greater than 0, less than 4, that is when it is decreasing. And then my f of x is greater than 0, so my y values are positive. Okay, my y values are positive when my x value is between -2 and 3, and when it is greater than 5. So this is all very interesting information that we're getting right now. It is going to be a little bit interesting to solve. I think actually what I'm going to do is kind of fix it over here and because I'm going to need more space for this problem. So I'm just going to kind of fix this up. So it seems like a lot of intimidating information, but all we need to do is just review the information we know about functions and their graphs, and then we'll be able to easily kind of sketch it. And again, the nice thing about sketching is that it doesn't have to be accurate. Okay, so the information that you're getting is very vague. It's just, so if you want to think of it as if I were to give this function to someone else, and I give them this information, they would know exactly what the graph should look like at certain points. They might not have the exact data or the exact information, but they at least have a general idea of what's going on. So what I just wrote in is now that the y values are less than 0, so meaning that they are negative values, when x is less than -2 and between the interval of 3 and 5. So now I'm going to look to sketch my graph, okay? So there's a general graph. It doesn't have to be perfect. I'm now going to use the characteristics to sketch the graph. So first of all, I want to mark key points. So here's my -2. Okay, then I had 3. There's 4. And there's 5. I think those are the main points, okay? So now I'm going to kind of go through left to right. So actually I should focus on where I'm looking at on my graph. So the first hint says f is increasing when x is less than 0. Okay, meaning that any value less than 0 is increasing. So we are going up. And then at 0, it's going to kind of stop. So once that point is at 0, no matter where it is on the graph, I don't have an exact y value, but once it hits 0, that's what's going to be called my turning point, okay? 0 is going to be that point where your function is neither increasing nor decreasing. It is going to be that turn. So what's going to happen is at 0, I am going to switch. Now, what I need to figure out, am I going to continue increasing or am I going to decrease? Typically, when you have a turning point, an end point in these inequalities, that is when you are going to switch from increasing to decreasing or vice versa. So from here, if I'm increasing, let me see, my decreasing says I'm decreasing when my x values are between 0 and 4. So my graph is now going to be decreasing. But now before I hit that 4, right, something happens at that 3, right? So I want to now look over at the 3 really quickly because I need to see what's going on at that 3. I do know that at 4, I am changing and continuing in an opposite direction, but I need to figure out what's happening at the 3. So 3 is affecting when my y's are positive or negative. So I have here that my f of x is greater than 0 when -2, between the intervals -2 and 3. So my y values are all positive from this -2 point over to the 3. Right? Then at the 3, what's going to happen is I'm actually going to now be in the decreasing section, right? Because when my y's are negative when x is between 3 and 5. So underneath here, we are living in the land of the negatives. My y values are negative. Then I'm at that 4, right? So it's kind of a lot going on that you have to remember what's happening, right? The main point is you figure out your key points on the graph, and then you figure out what's kind of happening around them, okay? So at that 4, I am now making that change. I'm at my turning point, and I am now going to be increasing because every value greater than 4 is now increasing. So it's going up, and again at that 5, that means that I have a 0 there, and then I am going to keep going. And that is basically what my graph is going to look like. So also when x is positive also when x is greater than 5, so that was your hint. Also, when x is less than -2, so remember that when it comes to less than -2, I'm looking at moving to the left, right? Even though when the larger the numbers in your negative, the smaller the actual value. So at that -2, as my values get smaller and smaller and smaller, my y's are still going towards the negatives. Okay, I feel like we are going to have a lot of questions about this. And actually, step 2 for this one is to identify key information. So my key information is going to be the degree, the leading coefficient, and the end behavior. So my degree is clearly going to be an odd value. Why? Because I end up in positive and negative end behaviors. My end behaviors are different, which is a characteristic of odd functions, right? If they went in the same direction, then that would be an even one. My leading coefficient, or my LC is positive because, and again, this is why I said it's very important to memorize that chart. A positive odd function is going to look like this. So that's what a positive odd function, the typical behavior is, okay? And then my end behavior, which I will call EB, is as x approaches negative infinity, y, or f of x, I should say, f of x is approaching, so again, as my x values are going to the negative, my y values are also going to the negatives. And as x is approaching positive infinity, f of x is approaching, and once again, as I am moving to the positive infinity, my y's are also going to the positive infinities. Okay, so sketching is a very abstract idea. We will be practicing that. I'm sure I will have a lot of questions about that. But now moving on to the word problem. So, modeling real life, the African wild dog is one of the most endangered carnivores on Earth. The estimated population of African wild dogs under human care can be modeled by the polynomial function. There it is, where t represents the number of years after 2000. So 5 years after 2000 would be 2005. So that's what the graph is going to look like. Now, the first thing it says is use technology to graph the function. So this part, this word problem, I'm probably going to be going over with you guys in person with the emulator that we have so that I can do the graphing calculator for you guys to see. But for now, I'm going to, oh, of course, I did this earlier. And no, it's not working. So here is what the graph is going to look like. This is in your textbook, so you can easily see it for yourselves. So I have now graphed it from the interval 0 to 18. So again, this here is my 0, or this is really, oh, yeah, that is 0. And then there's 2, 3, 4. So this is very horrible. Well, this is actually 1, right? Because it's 1, 2. So when I do the functions, I never like to do that 1. Just because, as you can see, the graph looks a bit funny. But that means that this line is 17 here, and this section right here is 18. So you can see it on the graph. Now, I'm going to describe the behavior of the graph of this interval. So how I would say that is that there's an increase from 2001 to, and I'm going to keep kind of watching it until I see that kind of shift where my function is going to go to a different behavior. So pretty much somewhere around 2007. So around 2007, my graph changes. okay? And so then it's now decreasing. Even if it's slightly decreasing, it's still decreasing to 2007, all the way until, I would say, personally, about 2013. You want to go a little bit before, so 2013. And then from 2013 on, it is increasing again. So when you do this kind of description, what you want to do is you want to read the graph left to right and discuss what's happening. Now, part B, so this was A, part B says, what is the average rate of change in the number of dogs from 2001 to 2018? Now, average rate of change, that's our slope, right? That's that y2 minus y1 over x2 minus x1. Now, on the graphing calculator, you will easily be able to find the values that you need. I'm once again just going to take the information from the textbook, which is where this question comes from. Now, remember that at 2001 is really when t equals 1, and 2018 is t equals 18. So when I plug this in over here, I'm actually going to do 18 minus 1. And then on the graphing calculator, I would get that this is 693.376 minus 384.418. Again, these numbers all are in your textbook. So if you have problems reading it from the notes, you can just get the information from there. So then I would have 17. And above it, oh, I'm not going to be doing that math, I guess. So I'll do it. Let me just give me one moment because now I'm going to have to type it in myself. So 693.376 minus 384.418. That's going to give me 308.958. And then when I divide that by 17, I get roughly 18.174. Okay, so that is my, which remember, when it comes to animals, people, things like that, you don't give decimal answers, you kind of round them to whole numbers. So 18, we would just want to say about 18 dogs. Okay, the rate of change is 18 dogs per year. So that's essentially what is happening. And then for part C, do you think this model can be used for years after 2018? So the problem with using such a small window and also these kinds of functions is that after I pass that 2013 and I start increasing on my graph, well, this is a cubic function, and I'll give you a hint. A cubic function will have two changes, right? It's going to have to look like this, meaning that this function is going to continue infinitely in that direction. And as we all know, unlimited growth is not a reasonable concept. So you don't want to use this model after that. And you can determine all this just from the end behavior, determining that it's odd, that the leading coefficient is positive, and all of that stuff. So you would not want to. So you can say it's fine for short windows, but unlimited is unreasonable. Okay, and so with that, that is 4.1. So please stay tuned for 4.2.